Hello and welcome to the Mechanical Engineering Design Fair. Today, we would like to present you a novel approach to controlling undesirable flow patterns in fluid dynamics. In fluid dynamics, a phenomenon known as flow separation can occur when a fluid interacts with a body having a particular geometry, such as the one shown here. Bodies with a geometry that favors flow separation are called bluff bodies, while bodies that are less disruptive to the flow and less likely to cause flow separation are called streamlined bodies. In this video, you see the results of one of our simulations illustrating one type of flow pattern that can develop when a fluid flows past a bluff body. Notice that after a while, the flow develops to a periodic state of vortex shedding. This phenomenon would go on indefinitely for a constant free stream velocity. Notice that as the flow develops, the lift coefficient on the cylinder oscillates periodically with the vortex shedding cycle. This load fluctuation can significantly impact the longevity and structural stability of engineering structures. From the work of other engineers and scientists, it is known that this effect can be suppressed by introducing a much smaller secondary cylinder somewhere on the wake of the flow. However, the position of this second cylinder is not obvious, as some positions could even end up amplifying this effect. Designing an algorithm capable of determining an appropriate position to attenuate the load fluctuations on the main cylinder is the main goal of our project. The applications of this design are very broad, and a few examples would be structures such as offshore risers and other underwater structures. Another potential application is urban design. As cities are immersed in air, introducing a building such as the Calgary Tower to an urban environment can significantly affect the local flow of air and influence pedestrian comfort. The methodology used to attempt to solve this problem consisted of creating a series of CFD simulations with the small cylinder at different locations, constructing a library of simplified models of the flow for each position, and then training a series of neural networks with these models to predict the flow for new positions. The flow of information in the algorithm looks like this. We start with the main cylinder and consider a finite number of positions around it. We separate a few for testing and run CFD simulations for all of them. From these simulations, we use an algorithm called proper orthogonal decomposition to generate simplified models of the flow from the results. The model has both a spatial and a temporal part. If the networks can predict the components of the model for an unknown position, this essentially allows for the simulation step to be bypassed, and we do not have to guess and check what the new positions will do to the flow. Based on our results, the networks were capable of predicting the spatial part of the decomposition for new positions relatively well, but the temporal part could not be predicted solely based on the coordinates of the new small cylinder positions. Here is a demonstration of how well the pressure field around the main cylinder could be determined using the predicted spatial components with the true temporal components of a test position. Since the lift coefficient on the main cylinder depends primarily on the pressure distribution around it, its lift coefficient can also be determined. And as you can see, the root mean square of the lift coefficient in the approximation is pretty close to the actual one. If a method of accurately predicting the temporal component of the model for a new position were to be determined, this process could be done for an arbitrary position, not just the one separated for testing. That would allow for a prediction of the RMS lift for an entire region of the flow domain, and a minimum could be located graphically. This is a very rich field and has gained momentum in recent years, and the application of neural networks to physical systems have a very promising future in science and engineering. Thank you for attending the fair and watching our video.